Hey, Will, here's that plywood you wanted. Ah, you wouldn't believe how windy it is out there. When I was carrying this thing over, it nearly picked me up.
Oh, it was because you were carrying it at an angle, and it's going to generate lift. You, of all people, should know that. Yeah, lift is the aerodynamic force caused by the motion of the air over an object or the motion of an object through the air. Lift is the force that counteracts weight. Everything from kites to birds to aircraft to Orville's piece of plywood will all generate lift as they're moved through the air.
Lift is generated by every part of an aircraft, but especially the wings. It's a vector force, which means it has both a direction and a magnitude, and is directed perpendicular to the flow, and it works through the center of pressure of the aircraft. Prior to our experiments in flying, my brother had written to Mr. Langley at the Smithsonian Institute and received all the technical information that was known at that time.
Yes, included in that information was a mathematical description of lift. This had been developed over 50 years earlier by Sir George Cayley in England. Here's what that lift equation looks like. Lift, L, is equal to a pressure constant K times the square of the velocity times the area A times the lift coefficient, CL. Now let's look at each one of these factors individually. K is called the Smeaton's coefficient, and it's a factor that describes the pressure. It's a factor that was developed in the late 1700s as a reference pressure value, equal to the drag on 1 square foot plate moving at 1 mile an hour. The velocity V is the relative velocity of the air over the wings or the velocity of the wings through the air. Those are exactly the same thing. A is the projected area of the wing surface. Projected area is the area you would see if you were looking down on the surface from above. The final factor is CL, the lift coefficient. This is a complex factor that includes a number of variables such as the shape of the wing and the angle of attack. It's usually determined experimentally.
Numerical values of both the Smeaton coefficient and the lift coefficient were included in the Smithsonian materials. The lift coefficients had been determined experimentally by Herr Otto Lilienthal, a German engineer and pioneer glider. He had experimented with the amount of lift generated on wings mounted on a rotating arm and developed a whole table of lift coefficients. Now, since we had both the values of the lift coefficients and we knew the lift that was needed to lift the weight of our aircraft, and we knew the flying velocity of where we were flying, we could then calculate the wing area needed to provide the lift to overcome that weight.
Yeah, but unfortunately, our first aircraft produced much less lift than we calculated. From our flight data on glide angle, we were pretty sure the CL value was good, so we suspected the error may be in the Smeaton coefficient. Working backward from our data, we arrived at a number of 0.0033 instead of the accepted value of 0.005 for the Smeaton coefficient.
By the way, the modern value is 0.00327, so we were very, very close.
Now, using this new value for K, we were able to better calculate the wing area needed for our new 1901 aircraft. The wing area increased from 165 square feet in 1900 to about 290 square feet in 1901. Unfortunately, the weight also increased from about 50 pounds in 1900 to close to 100 pounds in 1901. But both designs were made using the lift equation. That told us how big to make our wing area.
Right. We have to say something else about this lift equation. Besides being able to use it to calculate necessary wing area, we made another application. After the 1901 glider with its larger wings only developed about 1/3 the predicted lift, we built a wind tunnel and began testing different wing shapes in there and different wing combinations. We used small metal shapes like my brother shown here to work on the wind tunnel. And there we could develop a balance. We used old hacksaw blades and bicycle spokes. The balance would measure lift. We knew the value of K, we measured the area, we measured the lift, and we controlled the velocity of the air through the tunnel. So we could now calculate the value of the lift coefficient. It turned out that our values did not agree with Lilienthal's tables.
Using the data gathered in our wind tunnel, we began, though, to better understand what was wrong with our 1901 design. For one thing, our wings needed to be long and thin. We redesigned our glider for 1902. Weight increased a little bit to 120 pounds, but with this aircraft, we were able to become the most experienced pilots in the world. We had about 1,200 glides between the two of us. Should also note, Orv, that we decided to use rectangular wings for the additional strength provided from the Pratt truss structure, while Herr Lilienthal's design used elliptical wing models. Well, when we made a comparison between elliptical models and rectangular models, we found out that this shape has a big influence on the amount of lift and drag you get. We actually tested Lilienthal's model in our wind tunnel and found out that for his shape, he got his numbers pretty correct. His values of lift coefficients were right on.
We should also point out that the lift equation used by modern aerodynamicists, shown here, is slightly different. Smeaton's coefficient was a pressure factor, and more importantly, it's found that the density of air affects lift. So rho, 1/2 rho here, is used for the density of air. And you can see why modern airplanes, when they go higher in the altitude, have to fly faster, because they make up for less density. We were flying at sea level, so this wasn't a factor.
But I have one more thought about lift, Orv.
One more? What's that?
We've got to get out and lift all the rest of this plywood.
Oh.
Yeah, but I've got an idea how to make it easy.
Oh, you always do.
Yeah, well, we've got 2 sparrows, and we hang them.
English or African sparrows?
Oh, African sparrows.